this afternoon seminar. Well, I don't have words to introduce Professor Bernard, because he's a worldwide recognized scientist working in the field of network analysis. He's an anthropologist by background. And okay, he's the director of the Institute of Social Science Research at Arizona State University and emeritus professor of anthropology at the University of Florida. And we met in New York almost, well, let's say a couple of years ago. And that was a very nice occasion to apply and to understand how the network scale-up methods, and you will learn soon what is exactly about, to several different areas in public health in particular. And I also happy to have here Silvia Migro. She spent the first part of her life in network scale-up. She did her bachelor, master, and PhD on network scale-up, and she's coming here and she will start the discussion after Russell talk. So Russ, thanks again for being here, and please go ahead with the presentation.
So thanks so much to DARIO for the invitation to come here and tell you about the network scale-up method. It's nice to see some familiar faces, including Silvia. So let me right.
The other one.
No, I'm fine. I have two.
Okay.
This one has a PowerPoint, and this one flashes me words to remember. Okay, so this is that. Yeah. So here's a slide of the network scale-up team. You'll see Peter Kilworth is he died in 2008, very premature death. He was a theoretical physicist. His degrees were from Cambridge. He worked at Oxford and Southampton. He was a senior person in meteorological physics, earth geophysics. He was my research partner beginning in 1972. And then after, we added some of my students, Christopher McCarty and Gene Shelley, and Eugene Johnson, who is a retired professor of mathematics, a combinatoric algebraicist actually, at the University of California, Santa Barbara. But it's very important to make sure that we touch all these buttons, because this is a very, very eclectic team, and it was the whole operation was funded under grants from the U.S. National Science Foundation to me and to Christopher McCarty. And Doctors GREGORI and Sneeder
What is the problem? Because it was mismatching. Okay.
That's fine. That's okay. Sure. So Drs. GREGORI and Salinas were among the very first to apply the method to estimate the size of hard to count populations or impossible to count. And last year, 2021, there was an article in the Journal of the American Statistical Association that reported on the use of this method and the progress that's been made over 30 years. And I'm very happy to see that work on improving the method continues here in Padua, including that, of course, of the doctoral student, Ms. Osai. The method, however, is still a work in progress. So, as we seek to improve the validity and, most importantly, accuracy of the estimates of unknown size populations. And as with the early development of the model, these improvements requires collaboration. What you see here is the collaboration of survey researchers, McCarty, Shelley, Public Health, Gene Johnson, a combinatorics specialist, and my research partner, Peter Kilworth, a theoretical physicist. So that's what it takes to make more progress. And I hope that this will be the biggest lesson I can leave with you, which is to not be afraid to jump fully into true collaboration research with people far from your own field. Okay, more about this later. For now, let's go back to the beginning, how it all started. The network scale-up method was developed in conjunction with our team's research on the rules governing who people know and how they know them. In other words, the rules that produce social structure. That particular list of people whom people come to know in a lifetime may appear random, but the rules governing whom we come to know are surely not random. One basic component of social structure is the simple number of people whom people know. We call this number C. So the project began as a search for an elusive number of scientific interest, but at least at the time in the 1970s, of little practical interest. So I was working in Mexico City. It was October 1985. Just after the massive earthquake there, the government claimed 6,000 people had died. Opposition newspapers reported 4 or 5 times that many. What was the number? So in my work, I happen to be working in a government office, linguists and anthropologists working on indigenous languages. And one person told me, that number 6,000, that's just crap. We know many more people died because everyone knows somebody who died. So there have to be more people who are dead. That was the enlightening moment. Using a street survey, we asked 400 randomly chosen people in Mexico City if they knew somebody who had died in the earthquake. And 23% of them said yes. Well, so this led to a primitive model. I say primitive because after all, I am an anthropologist. I know my research partners have forgotten more about math than I'll ever know. So here's the model. If everyone knew the same number of people, and if there were no overlap in the people know, and if we knew the size of the bigger population in which some uncountable population of interest whose size E we wanted to no, university was embedded, then if we could find the probability that anyone in T, the total population, knew someone in E, the event population, then in theory we could solve for E. Well, as you can tell that this is a very big set of ifs. And so, of course, C is not a uniform number, it has a distribution. And furthermore, that distribution probably changes across societies and even across subpopulations within societies. So if we knew that distribution, then we could substitute M, the number of people whom people know, in the model for C. But we could substitute M for P. So to find C and its distribution, we asked a representative sample of people in T, the total, to tell us how many people they know in many subpopulations whose sizes are tracked reliably in public statistics, like people who are diabetics, gun dealers. In the United States, we have lists of them. Postal workers, women named Nicole, men named Michael. And then we use this maximum likelihood method to estimate the size of an individual respondent's network. This method for estimating C was due to Peter Killer's. And across 7 surveys that we did, we consistently found an average network of 290 people with a standard deviation of 232 and a median of 231. Notice how close that is. This 290 is not an average. It's a consistent finding over and over again. Well, we tested this. We were very surprised at that. And so we did everything we could to try and falsify it. We tried 3 different ways to disprove it. We estimated the number using a method of counting that was entirely different from the one we developed. We introduced error into the data to see how it affected the outcome. And we compared our results for C, across populations of known relative size. So, in one survey, we estimated C by asking people how many people they know in each of 17 relation categories. This method, by the way, was developed by Chris McCarty, one of our students, who's now a full professor at the University of Florida. So those 17 relation categories were people in their immediate family, people you know as coworkers, people who provide a service, and so on. And then summing up, it's called the summation method. It once again produced a mean of 290. In the second reliability check, we introduced errors into the data. We tested whether the changes in our estimates conformed to the changes we introduced into the data. For example, we changed reported values of how many people knew at or above 5 to a value of 5 precisely. The mean dropped to 206, a change of 29%. We set the values of at least 5 to a uniformly distributed random value between 5 and 15. We repeated the random change for large subpopulations with over 1 million people. The mean increased to 402 from 290, a change of 38% in the opposite direction. Well, in our third test of reliability, we surveyed a sample of clergy. We actually had a sample frame. Now, clergy are widely known in the literature as people who have very large networks. So they should have a bigger network. We used our original scale-up method and McCarthy's summation method. Here, the two methods produced quite different estimates of C, but both estimates are, as expected, larger than the 290 for the general population. So, that 290 wasn't a coincidence. Two different methods of counting produced the same result. Changing the data produces large changes in the results and in expected directions. And people who are widely thought to have large networks do. In each case, then, the results of our test were as expected, giving us some confidence in the estimate of C for the United States at that time. Now, this next slide shows the probability for two of our surveys. One, of knowing no one in 29 subpopulations, and the other one by the actual size. Well, yeah, the other by the actual size of the population. So these we tracked both of them and see how well they did against the things we knew. We knew 29 populations at the time of known size. This is quite a graph. And here is the graph of the distribution of network size. So we were measuring something, and we were doing it reliably. But if our model works, we ought to be able to use it to estimate the size of populations whose sizes are not known. Kilworth reasoned that we could create a maximum likelihood estimate for the size of unknown subpopulations based on what people told us about their network size. And that would be roughly inverting the other formula. So here's the sequence for applying the method. Ask a representative sample of people, how many people they know, in a list of populations whose size is tracked in public records. Estimate the size of each subpopulation after applying the maximum likelihood method. So we get a quantity C for each person. And then compare what the method predicts against the known sizes of the populations and to any alternative estimates that are available for the unknown size populations. And the next slide shows that the results we got were encouraging. Now note the two outliers in this graph, way up there, the upper left. And way above the diagonal. Those two outliers are twins, people who have a twin sibling, and diabetics, people who have diabetes. Now, when these two data points are removed, the correlation rises to 0.94. Who gets that in social science research? 0.79 is astonishing enough. But the problem is that the outliers represent something that needs to be accounted for. Just removing the outliers improves the correlation, but does nothing for the method. So you see that people tend to overestimate small populations, like people named Nicole, people who are undergoing kidney dialysis. So they overestimate small populations like that. And they underestimate big ones, big populations, like people who have a twin or diabetics. A valuable piece of information comes from this. In building a network scale-up survey, researchers should shoot for known populations, known size populations that are in a range of sizes. And from the work more recently by Matthew Solganic, we think that the range should be between 1% and 4%. We're making progress. Each incremental step is progress. We're not there yet. Here's another encouraging result. Charles Kadushin did a national survey to estimate the prevalence of crimes in 14 cities, large and small cities across the United States. He asked 17,000 people to report the number of people they knew who had been victims of 6 kinds of crime and the number of people they knew who used heroin regularly. And here are the estimates for the number of heroin users in each of the 14 cities, along with the estimates from the uniform crime reports of the FBI. In other words, when we can, we try to compare our results with other estimates that are this. So here we are. Here are the uniform crime report estimates for heroin use in the 14 cities are blue squares or circles. The estimates of the network scale-up survey are the red dots. These estimates are very similar. But the fact that we track well with official estimates means only that we have a much, much less expensive way to get at those estimates. Not that the estimates are correct. In fact, estimates of the other crimes in the 14 cities didn't track so well. So, while definitely reliable, and perhaps even valid, in other words, we're measuring what we think we're measuring, our estimates of network size and its distribution aren't sufficiently accurate. We've identified 3 sources of inaccuracy: transmission effects. Everyone, when we ask people about people they know who are in some subpopulation, they know the answer because everyone knows everything about everybody they know. Clearly, another big if. Barrier effects. Everyone in the total population T has an equal chance of knowing someone in the event population T. Clearly, another problem. And inaccurate recall. People don't recall accurately the number of people they know in the subpopulations we asked about when confronted by some survey researcher who just happens to show up with their door and ask. So, transmission effects, obviously, people don't know everything they know about their friends, family members, acquaintances. For example, you might interact with somebody you work with every day for years and not know that that particular person is a member of a particular church or suffering from some chronic illness. To learn these facts about people you know, they have to tell you. Not knowing things about people you know because these people don't tell you is the information transmission problem. A lot of information about people is blocked by both physical and social barriers. For example, here's a physical barrier. There are more American Indians in the state of Oklahoma in the US than there are in the state of Florida. So we expect people in Oklahoma will therefore know more American Indians on average than people in Florida. And in fact, they do. The P there is 0.0001. That's about. And there are social barriers. Black people are much more likely to be diabetic than are white people, and so we expect Black people will know more people who are diabetic. people in California are much more likely to know someone named Carmen. It's because there are so many people of Hispanic descendant in California. Other states have a low fraction of the population with Hispanic names. Now, we can address the barrier effect by using a representative sample of respondents T. The transmission bias, that comes from the fact that some things are more difficult to know about our acquaintances than other things. A stigmatizing event, for example, a suicide in the family. It's not shared with everyone knows. Some things, like having a twin sibling, may never come up in conversation, even among people who are close friends. We can study transmission bias by asking people why they do or do not tell their network members various things about themselves. And this will require sustained efforts in the collection and analysis of qualitative data. Here's an example. We asked 30 people if they knew someone named Michael and someone named Nicole, and so on. We chose the names so we'd have a good distribution, some common names and some less common. We kept asking people about first names until we got a hit. That is, the respondent said that he or she knew someone with that first name. We did that until we got 25 people in each of the 30 people's respondents network. Then we asked the respondent for some information about each of the 25 network alters. With 30 respondents and 25 alters, there were 750 alters. We were able to contact 220 of them and ask them things about themselves. Things that we had asked the original respondents about them. The next slide shows us a summary of the results. And we can see here, much easier to know someone in some populations than others. For example, it's much easier to know that someone is a kidney dialysis patient than it is to know that they're a diabetic patient. Diabetes is much less visible. In fact, 99% of people know their alters. Marital status. Egos know how many children 89% of their alters have. 98% know the employment status. But when we asked people about the number of siblings the alter has, egos say they don't know 52% of the time. And egos say they know the state in which 70% of their alters were born, but only 57% of the reports, that is, egos and alter reports are the same. So we know what the problem is. Now it's up to you and another generation of scholars to figure out how to make this work. We know what causes these tendencies to over and underestimate. But we don't know enough because we can't do this reliably. It's not just the size of the subpopulation. It's not even that some things are just because it's stigmatizing. For example, in the 90s when we were doing this, HIV was then a very stigmatizing event. So people in that time may have known people who were HIV positive, but not know that did not know about that because they just weren't told by their authors about their HIV status. Being a twin or a diabetic is neither stigmatizing nor, as in violent crime, newsworthy. So the fact that someone is a twin or is a diabetic may never come up in conversation, even after decades of noise. All of this, by the way, comes from ethnography. Hanging out, talking to people, having conversations with people about how they know people, how they know them, how they know things about other people. Here's another example from ethnography. Jean Shelley found early in the AIDS epidemic that people who are HIV positive withdraw from their networks in order to limit the number of people who know their HIV status. Eugene Johnson, mathematician at Santa Barbara, confirmed this, right, showing that HIV positive people had on average networks that were 1/3 the global average. The fact that people in stigmatized populations withdraw from interacting with some people in their networks was, in other words, found first in ethnographic research and then later confirmed mathematically. But it turned out that we weren't able to use this kind of information to tweak the model. We tried to develop weightings for classes of characteristics about subpopulations, classes like things that carry a strong stigma, things that carry a moderate stigma, things that just don't come up in conversation. And while we found some signals like this, we just don't know how to know whether two populations require the same weighting. Since we couldn't improve the model by using the information we collected about transmission and barrier effects, we turned to modeling the errors themselves. Shortly before his untimely death in 2008, Peter proposed the following. Instead of assuming that people are inaccurate, assume that they report accurately what they know. After all, you can see from this last slide, whatever the errors are in the model, this slide showing that comparing the results of two different populations, clergy and the general population, shows that whatever those errors are, they're consistent. So you can see from the back, you can see that Americans are very likely, I wish I had a pointer here, but you can see it, I'm sure it's big enough. They're very likely to know at least one person named Christopher. We also see that twins are probably underreported. The population of twins is very large. They're about 1 in 125 births. But about 30% of Americans reported in our surveys that they did not know anyone who has a twin. The problem is, we don't know what the truth is. We'd like to be able to redraw the graph in this slide so that the true values are represented. Not just what people report. How can we draw the curve on that jagged diagram so that the true values are represented? In other words, given the structure of the diagram, we decided, let's trust our respondents, assume they are reporting correctly what they know. It's just that what they know is incorrect. The jaggedy curve here doesn't tell us where the curve would be if people responded honestly to correct information instead of honestly to incorrect information. At the time, widows were 0.13% of the population in the United States. Suppose widows only tell half the people they know that they're widows. Then some people report that they don't know any widows. Those reports would be incorrect because they would be still reporting correctly what they knew. So to adjust for this, we would slide the x-axis in the graph to the left. Oops. While keeping the y-axis the same. That's a nice game you can play. Okay. Of course, we have no idea what the transmission error might be, how big an adjustment would have to make to the x-axis so for the jaggedy edge to go away. That's what we tried in vain to do with weightings. We only know that if the numbers remain the same on the x-axis and we make up the effective sizes on the x-axis, the jaggedy line would go. Well, this is another opportunity for research on the transmission effect. Finally, let's return to application of the network scale-up method. In the mid-90s, when we first tested the model, we estimated the population of people who are HIV positive in the US, and the homeless, and women in the United States who had been raped in the previous 12 months. Now, this slide shows that our estimates for those populations were very close to those made with other methods. And I should say, estimates from NSUM are often higher than official estimates. In fact, NSUM estimates, scale-up estimates, may be minimum because of the recall, transmission, and barrier errors. It was qualitative data that helped us identify those errors. Recall Gene Shelley's discoveries about the networks of HIV people shrinking inside because of stigma. We also discovered, from talking to people, cognitive interviewing about the method itself, we discovered a rounding effect. How many people do you know named Michael? This may result in an underestimate because of poor recall, or an overestimate because of rounding. That is, people say to themselves, well, I can count 3 Michaels I know. It's a very common name. I must know more. I'll just say 5. If you do the cognitive interviewing, you'll find things like this in the surveys you're doing. All of that is data to help us improve research. What we need is sustained research, like the work of colleagues and students here at Qualitative, that tackles all the pieces of the puzzle and compares the results of each purported improvement to estimates of known size populations. And what we've seen over the last 30 years is that the network scale-up method is used for making estimates of many, many different hard-to-count populations. And I'm very happy to see this. But from the beginning, we could see that the need was for practical solutions to the problem of measuring hard-to-count populations, and that need took precedence over the need for more science to improve the method. When we published our first papers on the method in the late 1980s, in 1989, the United States invaded Panama. I got calls from journalists asking, "Are you the Dr. Bernard who estimated the number of earthquake victims in Mexico? Can you tell us how many civilian casualties there were in Panama?" I got calls from advocacy groups asking if the method could be used to estimate the number of women raped last year in Seattle. I would tell everyone the same story. Please help us, support us to do a survey that will both estimate the populations you're interested in and improve the method. No one wanted to help. They just needed numbers or answers to politically and morally important questions. The help we needed came from the National Science Foundation, and this led in 2008 for UNAIDS to use the method in several big national surveys around the world, including, by the way, in Ukraine, where they've just repeated the whole effort. It's being used by UNAIDS to estimate the size of populations for particular vectors of HIV. Female prostitutes and men who have sex with men. And that's it. Thank you.
Ask Celia to make the discussion.
I'm very honored here to you because I spent before the first year of my book in studying Scalab method. And I totally changed work now, and I wanted to read the last 15 years in maybe 2 days of the papers published in these 15 years. It is impossible because a lot of people work on the Scalab method. I was quite surprised and very happy about it. And
You couldn't be happier than I am. It's fabulous.
It is really interesting to listen to also because it's a different way your papers and listen your history. You told us that you meet the other professors and how you get your results. And a lot of models are now available of different types. Fragmentist, Bayesian, with good results. There are also still the problem of transmission, barrier, and we call it bias.
Yeah. Yep.
But a lot of work was done about it. And maybe, in your opinion, what's the first thing now? The next step, we can start to do new research, for example, to minimizing, in order to minimize these biases. What's first? Because biases, transmission effect.
I wouldn't know how to answer that question because I don't have the measurement. That's the whole idea. We need just be clever and brave. Clever in the sense of thinking up interesting ways to test these boundaries, the error bounds of the instrument, and brave enough not to listen to anybody who says, well, you shouldn't do it. It needs a lot of research. It's thrilling to me to see that this is a worldwide effort and that people are engaged in it. there are people in China, Iran, Brazil. It's wonderful. And but you should know that in science, we make incremental steps. The incremental step is important. If you pile enough of them up, somebody is going to have an interesting idea about what's tracking everything, what's pushing everything from behind. I just don't know the answer. I know that the effort to find the answer is thrilling.
And for your experience, and for the next 30 years, what's your dream about this kind of method? What do you see? A golden model useful for all kinds of that can control all the biases?
Yes.
Or maybe a protocol. What do you think that it will be? A protocol with that kinds of models, or just one?
I have no idea.
No idea.
No, my plea to you is not to try and find the answer to that question. You'll wind up doing a lot of spinning of wheels. Just think of really clever ways to test things that attract your attention of things to measure. Like any bias, whether it's recall bias or transmission bias or barrier bias, whatever those are, there's research to be done. It's 30 years means that there's now several generations of scholars have worked on this. You can just see the work of Matt Salganic and his students, and Dennis Feehan and Tyler McCormick. And these are people from very different positions in sociology, in mathematics, in statistics. They have different perspectives, and that's the big lesson is that you should be thinking of interesting, clever ways to solve very small problems, not something that's going to change the world. A new model. If a new model occurs to you, publish it, test it.
Just add to what Sylvia said and what you have said. Okay, we have to say we have an experience in applying the scale up in several fields, and some of them were new ones.
Mm-hmm.
In the public health or healthcare service research, we estimated the number of people who were not satisfied by the service they got in the hospital.
Mm-hmm.
This could be a kind of stigmatizing question, because some people, particularly older people, are afraid to say something against the hospital just because they say, okay, maybe I will face again another hospitalization and want to hurt anybody. And it worked. Then we use that for injuries children. Again, because here could be a problem for parents to say directly what they mean, what happened to the children, because it may be associated with bad or insufficient care or attention. I have to say, however, that doesn't, I mean, in our experience, all these methods are working well, and people are answering to the questions much easier and much more comfortable than they do with direct questions. But what they suffer normally is about the set of questions about the known population size. Those questions are the toughest one to get through when you ask.
Mm-hmm.
So maybe there is also, how can I say, another, the fourth type of bias, which is the bias regarding the stopping the survey, stopping it to answer because of the length of the
Right,
questions.
sure.
And so for some population, we may not get that. So we ended up to publish a paper a few years ago that randomizing the order at least provides us some information
Right.
on each of the subpopulation. Maybe if you average across all the answers, you can get an idea, but maybe not precisely for that person, but in general.
Yep.
In general. The second point is that in some field of application, the biggest trouble in using NSUM is that you have to fight against the reviewers, because in particular in health or medicine field, well, it's kind of difficult to get that the methods be accepted, and usually you have to have a strong interaction with the editor for
Right.
several rounds of
Right.
back and forth discussing. And you have to prepare, saying this to the youngsters, if you use this method, you have to be prepared in certain field to be very, very sticky on your points, because
Absolutely.
it's not it's not in the mainstream.
Right.
I mean, in medicine, in public.
Right. Yeah, that's why I said you have to be clever and brave.
Yeah, you said it. Good. And any other people have any questions?
By the way, I should tell you that, I've read Noria's thesis, and the random, asking that random question is, it's a very good idea. It needs to be replicated. That's all that's an important thing. If you replicate that, and there are obvious ways to test it. You could model this by taking average of what people answer and doing computationally, right? And then you could average you could do that by randomly selecting from 20 known size populations. In fact, Peter did some modeling of that, and we know that with 20 populations, it's more than enough to replicate everything we did with 29. But 20 is a lot, especially if you're doing a survey that is not just about NSUM. So one of the obvious things to do would be to test what the minimum is that you need in order to make estimates that are within parameters that public health requires. We set the parameters yourself.
Our idea was also to make separate the two steps.
Mhm.
And deriving the distribution across the population of the known
Yeah.
sizes, and then use by methods.
Yeah.
And use that just one answer to one question to anchor, let's say,
Yeah.
the specific person to the specific.
Right. Now, if you do that, and you do 15 or 20 replications against against a full NSUM study, you'll know the extent to which cutting it down to one question is enough, or whether 2 or 3 or 4 might be perfect, and whether they have to be randomly chosen or not randomly chosen. These are things that can be tested in surveys. And since there's a big tradition of doing public health surveys here, if you just tack on that as an extra to test from many public health surveys, you'll find answers to those questions.
So other.
Just a curiosity. Recent year, in South Korea, we provided to uncountable. Do you have any suggestion?
I'm sorry, I can't hear. Can you? I'm sorry, I couldn't hear you.
In recent years, the survey are implemented for uncountable. Do you have any suggestion to provide something suitable forms?
Of the survey?
Yeah, online.
Yeah,
web server.
yeah. Well, to me, this is one of the things that's easiest to do. And you can do it with, you know, some of the social media, like Twitter, allow you to do with an API. You can grab, they'll give you large, for research, large chunks. And then you can do that online, and you can do it with replicating it many times, but just asking people the same question. So online to me would be like the very obvious thing to do with this, because it's so much easier to replicate.
But you need to get an estimate of the known sizes population on the basis of the Twitter data.
You could do that if you ask them those questions.
Yeah,
Right.
because looking at the words they use, or with the
I'm not sure. I'm saying this is the kind of clever stuff you really want to do. Or you could use the known size populations and simply throw in one or two unknown. You can do the NSUM, replicate it many times with subsets of randomly chosen subsets of Twitter or Facebook users. It's hard to do because they don't provide enough information about the people who are answering the questions. So it's hard to know whether or not that would give us answers about whether or not things are stigmatizing or not. But yeah, it would be the next obvious step would be to do many replications on the web. In fact, you know, you can do with Amazon Turk. You can have thousands of people taking surveys for pennies a piece. So yeah, I would turn to that. I would also recommend doing a lot of this work to modeling, so that you produce questions that can be tested in real life, where real life could be Twitter. Doesn't have to be face to face. Did I answer her question?
Two questions. The first one, do you have some confidentiality problems?
I'm sorry, I can't hear again. Could you remove your mask?
Confidentiality problems.
Can you remove your mask?
Have you ever had a problem with confidentiality when you conduct this sort of studies?
No. No. The answer is no. Any surveys that we do have to go through what's called institutional review board. So we can't do surveys without that, right? So
you are asking people about the network.
yes.
Social network. So
Yeah.
you are asking for that.
I never ran into that problem, but I can see where it could bother some people. But you know, under IRB rules, that would not be a problem.